My name is Alexander Smith, and in this breakout session, we're going to take a look at how Formula One cars survive extreme G-forces using SOLIDWORKS simulation to study an F1 car's suspension. And straight out of the gates here, I want to mention that if you have any questions during this session, you can move over to the Q&A tab of Excel events to ask anything, and either myself or my colleague Patrick will answer you as soon as we can. Now, the goal of this session really focuses on the design requirements for a Formula One car. In F1, you can only earn points if you actually finish the race, and so the car's reliability is paramount. Along with that, the car's performance is obviously critical, and so as an engineer tasked with designing an F1 car suspension, which is what you're looking at now, you'll have to strike a balance between durability, weight, and then, of course, handling characteristics. For this design, we have three main goals that we will strive to achieve. One is to keep the stress below 400 megapascals and the factor of safety above 2 for the pure strength aspect. Another is the durability, or ensuring that the steering bracket can last for a full season or 100,000 cycles. And from a handling aspect, we want to ensure we aren't transmitting vibrations from the wheel through the system that would cause it to resonate. So we need to check that the resonance frequencies aren't within the 1 to 60 hertz range, which is a common vibration frequency the components will endure while racing. Now, as far as what I hope you'll take away from this presentation, that'll be simplifying the assembly by only including components critical to the study, representing any missing components using proper fixturing, applying load conditions to represent real-world situations, and how to strike a balance between simulation result accuracy and running time. With that all being said, let's go ahead and jump into SOLIDWORKS. So here we are in SOLIDWORKS, and this is the full F1 suspension assembly, including the main components like the upper and lower wishbones, the steering tie rod connected to the steering bracket, and then the knuckle, as well as many others. Now, the first important thing to realize when simulating an assembly is that an assembly as complex as this one would take a ludicrous amount of time to run any simulation studies on. And so, because I'm mostly concerned with the steering bracket itself, the first thing I'll do is swap over to a configuration that includes only the steering bracket assembly. All right, so there we go. Just have the steering bracket assembly now. And provided I do a good job of representing the other critical components properly using fixturing, using this simplified configuration of the assembly should still give me valuable results in a fraction of the time. Now, in SOLIDWORKS simulation, if you're just starting out with it, there are some minimum requirements we need to meet in order to run a study. That is, we need at least one material, fixture, load, and a mesh. And I'm going to show you how to add all four properly. I'll start by creating a brand new study. And thinking back to our design requirements, I first want to check the design strength. And so I'll create a static study to do so. Looking through my simulation tree on the left here, we can work our way from the top to the bottom in the tree to set up the study. And at the very top, we have our parts folder, which I'll expand. In the parts folder, it just shows us all of the components in the assembly. So we have the steering bracket, the steering rod and ball, and then the pin that connects them together. You can see that the steering rod and ball and the pin both have a green check mark next to them, and that just means that they have a material applied to them already. Meanwhile, the steering bracket does not have a green check mark, meaning it doesn't have a material applied to it, and as I mentioned earlier, all of our parts do need a material applied to them in order to run the study. So let's apply a material to that steering bracket. I want to use a 6061 T6 aluminum alloy, so I'll search my library for it and apply the material. All right, so the steering bracket now has the green check, so we can move on to the next section in the tree, which is connections. Now, these connections are used to define how your components interact with one another. By default, we have this global bonded interaction, which means that any components contacting one another will be bonded together, which basically means they're glued or welded. We can leave this global bonded interaction as it is a good approximation of the actual interaction between components. We'll look into adding other interactions later in this session. So leaving the connections as is, next we have to decide how we will restrain our system using fixtures. I know that the knuckle component is what keeps this steering bracket fixed in place, but since I haven't included the knuckle in the study, I have to represent the knuckle using fixtures. Now let's take a look at a configuration that includes the knuckle so we can get an idea of how they're connected to one another. So in this other configuration, we can now see that the steering bracket is fastened to the knuckle using these 3 screws. And the two components butt up against one another on these flat faces where they touch. And so I'm going to go ahead and represent the knuckle using fixtures because I haven't actually included the knuckle in the study. So back to the steering bracket configuration here. For now, I'm going to assume that the bracket is rigidly flat against the knuckle, and I'll represent that using a slider fixture on the back face. So I can go ahead and go to my fixtures, select the slider fixture type, select that back face, and apply the fixture. Now, as you can see, we have these green simulation symbols that appear. And so what these are is the simulation symbol for fixtures, and they just show you which direction is constrained or fixed for that particular face. The bracket is also fixed to the knuckle with 3 bolts, and to simplify that connection, I'll assume the bolts are rigid without any preload, which is represented by a hinge fixture on the 3 cylindrical faces. So going to my fixtures, I can select the hinge fixture type, and then select my 3 faces. There we go. And that's it for fixtures. So know that now that our bracket is fixed in place properly, we can move on to the external loads that will be acting on it. To simulate the driver turning the wheel, I'd like to represent the tie rod applying a force on the steering rod and ball as the car takes a corner. And I'll do that using a force load applied to the spherical face of the ball. So I'll go to my external loads, select the force load type, and like I said, we want to apply this to the spherical face of the ball here. And by default, it will apply the force normal to the selected face, which is not what I want. Instead, I want this force to be applied along the axial direction of the tie rod. But as we can see, the tie rod hasn't been included in this study. So instead, for the selected direction, I'll choose an axis that I actually created earlier before this session. And this axis runs along the length of the tie rod. And so with that axis selected, you can see that I'll be applying this force along the axial direction of the tie rod without even including it in the study. And for the magnitude of the force, which is the last step here, I had to do a little bit of research. So let's take a look at this clip of Lewis Hamilton driving around Mugello back in 2020. Now, I want you to keep your eye on the center of Hamilton's halo, where it currently says 0.6 G. This area just shows both the magnitude and the direction of the G forces that the car and driver are feeling. So let's take a look. All right, and as seen in the clip, the car sustains over 4 lateral Gs for several corners in a row and hits a peak of 5.6 lateral Gs. Can you imagine that? Having to drive a race car while feeling the force of nearly 6 times your body weight pushing on you? It's pretty incredible to say the least. Now, back to our simulation, I'm going to apply a force of 12,000 newtons, which is the peak load it would see from steering inputs during a race. And this is going to be along that axial direction. All right, and so that's the external force applied. The last thing we really need to do here is to create the mesh. Now, basically, for this mesh here, you can use this slider at the top to change the mesh density, making it more coarse or fine based on your needs. You can also modify the mesh parameters, which gives you a more precise control over that mesh density. I'm going to leave these settings as is for our mesh. You can also decide between a high quality or draft quality mesh. Draft quality elements are about half the nodes of high quality, making them great for a quick first pass study when dealing with complex components that would otherwise take a long time to simulate using a high quality mesh. And so for this study, the bracket is pretty simple. So a high quality mesh will still be quick to run. And so I'll leave it as a high quality mesh and create the mesh now. And once the mesh has been created, it places a mesh result plot on the model so that you can see what the mesh looks like and decide for yourself if the mesh is fine enough or not. For our study, this mesh will work well. Just remember that the finer the mesh is, the longer the simulation will take to run. All right, now thinking back to our minimum requirements that I mentioned at the beginning, we needed 4 things to run a simulation. That is the materials, fixtures, loads, and a mesh. We now have all 4, so we can go ahead and run the study. It's just going to take a few seconds to run here as it is relatively simple. There we go. And once the study is complete, we can see our result plots shown at the very bottom of the tree. And starting with the von Mises stress plot, it colors different areas of the model based on how much stress is being seen in those individual elements, corresponding to the legend on the right. Now, we're concerned specifically with the maximum stress being seen in the model, which this max flag displays as 318.6 megapascals, which is well below our target stress value. Next up, the displacement plot shows how much the elements of the model move under loading. And our maximum displacement is around 0.2 millimeters, which is fine for our purposes. Now, displacement wasn't one of my design requirements, but since the plot is created automatically, it's a good idea to take a look at the results and make sure they're acceptable. Now, other than the maximum stress, I'm also concerned with the factor of safety, which, if you're not familiar, factor of safety is simply a ratio of the material's yield strength to the stress seen in the model. Basically, if you have a factor of safety that is below 1, that means that the model has failed under those loading conditions. But if you have a value greater than 1, then it has not yet failed. Generally, you want a factor of safety of at least 2, which is what we're aiming for here. So I'll start by defining my factor of safety plot with the default settings. And just like the stress plot, it's going to color the model based on the factor of safety values being seen in each element, corresponding to the legend on the right once again. And as we can see, the minimum factor of safety is 2.63, which is well above the target value. And that means that if you multiplied the force load value of 12,000 newtons by 2.63, then our design would just barely fail. Whereas if the loading was any less than that, it will not fail. So with this static study, we have confirmed that the design is sufficiently strong. So let's move on to studying its durability. In order to study the design's durability, I'll create a new fatigue study, which will allow me to see how the design will fare over a full Formula One season. So on my new studies, I'll select fatigue for the type and create it. Now, fatigue studies are used for seeing how much degradation we experience if we keep repeating a static loading cycle. Basically, the fatigue study involves punching in the static study's result into an SN curve from the material and seeing where it would lie after a certain number of cycles. So I simply add an event here for the loading, which selects the static one study we just completed automatically. Then I tell SOLIDWORKS how many cycles or repetitions of the loading scenario from that static study I would like to put the design through. And I did a bit of math here, and based on the number of corners at each track, the number of laps completed each race weekend, and the number of races during a full Formula One season, the steering bracket will have to undergo roughly 100,000 cycles. So I'll plug that value in, and that's all the information that is needed for this fatigue study. It's super basic to set up here. And so I can go ahead and run the study. All right, it's done already. And the results of the fatigue study come in two forms. First, we have the damage plot, which tells us how much damage the model has taken. And in ours, we can see that our steering bracket here has taken around 2.5% damage in the worst areas shown in red. And next up, the other form the results take is the life plot, which tells you how many cycles your model would withstand before failing. And as we can see from the life plot, we have a minimum value of 4 million cycles. So the areas in blue can withstand 4 million cycles just about anyways before failing. And that's going to be far more than we would ever need. Remember, our target was 100,000. Realistically, though, this bracket would never see the full 4 million cycles it would take for it to wear out, because it will either be replaced at the end of the season when the team builds the car for the new season, or more likely, the driver is going to crash into the wall, destroying the component and prompting its replacement. So, with the fatigue study done here, it's very safe to say that our design is extremely durable. And so next, I'd like to check our design for performance. Or more specifically, I want to ensure that the rotation of the wheels and running over curbs will not cause the bracket to resonate, which can be done using a frequency study. So I'll create one now. And the frequency study requires all of the same setup as our static study. But instead of creating everything again, I can simply go to my static one study, select my parts, fixtures, and loads, and simply drag and drop them to my frequency study. And that copies them over so I don't have to create them again. And with that, that's all I need to do here. It's already in setup, just basically from everything I pulled over from the static study, so I can go ahead and run it. Now, frequency studies do take a little bit of time to run. So in the meantime, let's take a look at what we're trying to avoid. What I'm going to show you here is a clip of Esteban Gutierrez running over some curbs back in 2013. I want you to watch his front and rear suspension as his tires run over the curbs. All right, so as seen in the clip, Gutierrez suspension vibrates wildly when he goes over the curbs, which we definitely want to avoid in our design. So let's go ahead and see how ours will do now that the frequency study is done. Now, the frequency range we want to avoid is between 1 and 60 hertz, which is the range of vibrations caused by the car running over curbs like we saw in the video. The results for the frequency study take the form of the first 5 vibration modes. I'm currently looking at the first vibration mode, which would have the lowest frequency. I can animate this vibration mode to see what it would look like in the real world. And so basically, it has the ball oscillating up and down. And this would occur if you passed a vibration with a frequency of around 2300 hertz through the component, which is obviously well above our 1 to 60 hertz range. You can go ahead and check out the second mode shape as well and animate that. And this mode shape shows it going side to side around 3400 hertz for the frequency. I can take a look at the third mode shape and animate that too. This one's a bit interesting. It shows the ball sort of twisting side to side at around 7400 hertz for your frequency. Now, you don't have to go through these one by one. Instead, what I can do is just list out all of the resonant frequencies. And based on this table, I can take a quick glance at it, see that none of these frequencies are anywhere near our 1 to 60 hertz range, and we can confirm that, well, this study is a success. We're not going to be resonating this assembly here based on driving over curbs. Okay, so basically, now that we've confirmed that for performance, for the design for performance, we've met our goals there. Basically, that's about it, right? Now, it's at this point that you could be satisfied with the simulation results and walk away. However, if you remember back to the first thing I did in the static study, I swapped to a simplified configuration of the assembly that only included the steering bracket. So to confirm the accuracy of these simplified studies, I'm going to rerun the static study, but this time including more components in the assembly. This more complex static study will take much longer to run, but it should produce more accurate results. Once it's finished, we can compare the results to the first simplified static study, and based on how close the results are, we can decide whether the results of all of the studies we ran are valid or not. I'll start by swapping to a configuration that includes not only the steering bracket, but the knuckle component as well. And then I want to create a new static study just like this first static study we created. But instead of creating a new empty study where I'd have to redefine the fixtures, loads, and materials, I'll instead create a copy of the first static study. I'll go ahead and name it static 2 because I'm not very creative. And I'm going to make sure that for the configuration to use here, I'm going to go with the one that includes the knuckle. And so here we are in our static 2 study, which already has the materials, loads, fixtures, and even the mesh taken care of. Obviously, we're going to have to do another mesh because we have the knuckle, but still it tries to bring it over all the same. Now, in the first simulation setup, I simplified the study by assuming that the bracket is rigidly flat against the knuckle, and that the 3 bolts were rigid without any preload, allowing me to use a slider fixture on the flat faces and a hinge fixture on the cylindrical faces, while leaving the knuckle and bolts out of the simulation altogether. Now, assumptions are necessary in simulation studies, but the less assumptions and simplifications you make, the more accurate the study will be. So in this study, I'm going to include the knuckle component in the simulation, allowing me to represent the interaction more accurately between the flat faces of the 2 components. It also allows me to use bolt connectors in the 3 holes, which will be much closer to what takes place in the real world. So, to better represent the contact between the knuckle and the bracket, I'll add a local interaction. So this is under my connections here, a new local interaction. And instead of manually selecting it, I'm going to use the automatic option here. And what I'll do is simply select the 2 components. So that's the knuckle and the steering bracket. I can then hit find local interactions. And what do you know? It finds an interaction on those 2 flat faces there. And so all that's left to do here is choose the interaction type from one of these 3 options. And for the type here, I'm going to go with contact. And what that means is that the 2 faces are not bonded together, and also they cannot penetrate one another. So that'll be just like the relationship in the real world. If that doesn't make any sense, just think about your 2 hands, for example. They're definitely not bonded to each other. They can move away from each other, but they cannot move through one another. So that's what a contact interaction is. All right, so I can go ahead and add that, and I can find it under my connections in my local interactions. There it is, that local contact interaction. Now, with this new interaction I've just created, it effectively does a better job than the slider fixture, but it covers the same bases, right? So I can now remove that slider fixture as I no longer need it. Important to note here that a contact interaction takes much longer to solve compared to a bonded interaction, which is why the global bonded interaction is there by default. And we simply add local interactions where we want to override the global interaction. Next up, I'd like to properly represent the bolts in the assembly, including preload this time. I'll start by deleting the hinge fixture since we won't need it anymore. Just like with the slider fixture, we're going to be replacing it with these connectors. And so now the best way to represent the bolts isn't actually by including the components in the study, but instead to represent the bolts using bolt connectors. So I'll go to my connections, select the bolt connector type, and then basically I need to choose what type of bolt or screw I want to use. Now, these holes here that connect the 2 components together are blind holes. So they do not go all the way through the knuckle. And so you wouldn't be able to use a nut and a bolt. Instead, we have to use a screw that will thread into the threaded face in the knuckle. So I'll set it to counterbore screw for my type. And then it's pretty simple. You just have to select the edge on the front of the hole there. And then after that, just select the cylindrical face where the threads are going to be. So that's the cylindrical face of the hole in the knuckle. And based on those selections, SOLIDWORKS automatically picks up the head and shank diameter of the fastener or screw you're going to need. I don't need to change those. The defaults are good. I want to make sure my connection type is distributed, not rigid. For the material, I'm going to go with a steel alloy. And finally, at the bottom, we have our preload information. As I said, I want these screws to have preload applied to them. For the screws I'm going to use, I'd like to torque them to 42 Newton meters. So that'll be my preload torque. And the coefficient of friction is going to be 0.125 for these screws. All right. And so I can now apply that very first bolt connector. And then I have to do that 2 more times for the other 2 holes. Now, thankfully, I don't have to put in those values again. They stay the same. So all I have to do is make the selections of the edge and the face for the both of the other 2 holes. And there we go. I can now get out of here. And as you can see, those 3 screws show up in the graphics area in that blue color. And also you can see them under the bolt group, the 3 counterbore screws that I created. Okay, and so finally, the last step we need to complete before running this study is adding in fixtures once again, because of course we've removed all the fixtures and they are required. And so without any fixtures, the component would simply float around in space when the load is applied. And knowing which fixtures to add is critical to creating an accurate study. You don't want to just throw random fixtures in. And so what I'm going to do is take a look at the full assembly to see what components will fix the knuckle in place and how. Okay, so looking at the full assembly now, what we can see is that the knuckle is fixed in place by the ball joints on its top and bottom faces. So just like I represented the knuckle in the first static study by using fixtures, I'll represent the ball joint using the same fixture types. I'll swap to another configuration with less components here to get a better idea of what we need. All right, so this one's a bit easier to see. So as we can see, each ball joint is connected to the knuckle on its top and bottom faces using 3 bolts, which for simplicity's sake, just like the first study, we will assume that these bolts are rigid without any preload and represent them with a hinge fixture. So we're just making simplifications. And we also have this cylindrical boss on the ball joint that matches up with this blind hole in the knuckle. And we're going to represent that with a hinge fixture as well. And finally, we will assume that the ball joints are rigidly flat against the planar faces of the knuckle on the top and bottom and represent that using a slider fixture. Okay, so moving back to the configuration we're using for the simulation with just the knuckle and the bracket, I'll add in these fixtures. So first, I'm going to add in the hinge fixture. All right, and so this is going to go for the top anyways on these 3 bolt holes, as well as the cylindrical face of the blind hole. And then I can't forget about the 4 on the bottom as well. Same selections, the bolt holes and the blind hole. There we go. So I've added in that hinge fixture. And then to finish this off, I just want to add a slider fixture to the top and bottom faces, right? And that's going to simulate the contact between the 2 components. So slider fixture on the top and the bottom. And there we go. That fixture is being added. Okay. And so the knuckle is now properly fixed in place. And of course, the 2 ball joints have now been represented in the study without actually including the components themselves. And so with that, I can go ahead and create the mesh here. Now, this mesh is going to take a little bit longer than before because, of course, with the inclusion of the knuckle component, there is another component to mesh and it's much larger, so it takes a lot longer to do so. There's a lot more mesh elements that need to be created. And once the mesh is done, I can go ahead and run this study. Now, with the first static study we ran, it actually took less than 4 seconds to complete due to the relative simplicity of the components and connections included in the study. In this second static study, it will take far longer to complete at around 17 minutes. And this is due to the complexity of the contact interaction between the flat faces of the knuckle and the bracket, as well as the inclusion of the knuckle component in the study, which results in almost 11 times as many mesh elements that need to be solved. So instead of waiting 17 minutes for the study to complete and wasting everyone's time, I'm going to cancel this study, just terminate the simulation, and instead what I'll do is I'm just going to switch to an assembly that I created this morning that already has the static study completed on it. And so it's an identical assembly here, nothing's different. The only real change is that the actual study has already been run, so we don't have to waste any time on it. Okay, and so now that we're in the completed model here, what we can do is take a look at the resulting von Mises stress plot. And what we'll see in this stress plot here is actually a little concerning. And that's because we can see that the location of the maximum stress has moved to the edge of the bolt holes. And this behavior is actually normal and expected, as the combination of the preload torque in the bolts and the sharp edges of the holes create what is known as a stress concentration or an FEA artifact, which tends to be inaccurate. You can dig deeper into the stress concentration to get more accurate values by filleting the edge or using a finer local mesh in the area. But in most cases, we can ignore this stress concentration and instead focus on the location where we had our maximum stress from the first static study, which is exactly what we're going to do here. So what I basically want to do is find the amount of stress seen in the static 2 study at the precise location of the maximum stress seen in the static 1 study. Due to the stress concentration at the bolt holes, however, the maximum flag we've been using to identify values thus far will not work as it's at the wrong location on the part. So to get the correct location, what we're going to do is go back to the first static study. I will activate the configuration. And what I'll do is I will probe the von Mises stress plot. Oh, looks like it just needs to be run again really quick. And in the von Mises stress plot, I'm just going to probe it. And what that's going to allow me to do is effectively with the probe, it just lets you point and click anywhere on the model in order to figure out what the simulation results are at the location you click on. So what I'll do is I'll click on the maximum stress location. And of course, the node it creates with the value isn't actually helpful at all because we already had that value. But the point is, what I can now do is I can save this probe location as a sensor. So I'll save it as a sensor, hit OK, and then I can go back into my static 2 study. I'll activate that configuration. All right, and now I'll go into the von Mises stress plot, and again, I will probe it. But this time, instead of pointing and clicking where I want to probe for the stress value, I'm going to reach back into the static 1 study and use the sensor that I just saved as my probe location by selecting the From Sensors option. And that allows me to probe the exact location I probed in the first study, which was where we had our maximum stress value. And once probed, we can see that the maximum stress is 318.2 megapascals, which is very close to the 318.5 megapascal maximum stress seen in our first study. I can also go into the chart options here and make a quick modification to the von Mises stress result plot, because by default, it's going to automatically define the maximum value for the red color in the legend. And so what you're seeing is that around 520 megapascals is where you'll have that red color. So of course, in that corner where we're seeing around 318 megapascals, it's not red, it's green. And so these two result plots between the two static studies don't really match up because of the stress concentration. So if you want to override that, I can simply change the maximum value to be 318.5. And now the colors on the static 2 stress plot will match up and be comparable to the static 1 stress plot. All right, I can also do all this in the factor of safety plot. So I'll do that. I want to check if the factor of safety has changed or by how much. Once again, the minimum flag will not work because of those stress concentrations. So I will probe the factor of safety plot. And from the sensors here, I'm going to go ahead and take a look, and we can see the factor of safety at the probed location is 2.63, which is actually identical to the value we got in the static 1 study. Okay, and so with all that comparison that we've just done here, let's take a look at an overall result comparison for physical strength. First up, let's compare the maximum stress and minimum factor of safety from both of the static studies. As we can see here, we have a difference of 0.09% for the maximum stress and a virtually identical minimum factor of safety. This validates the accuracy of the simulation studies that we ran using the simplified configuration of the assembly. Meanwhile, the second static study involved an increase in the number of mesh elements by nearly 1,000%, while the time to solve the study increased by over 34,000%. So, altogether, the second static study should technically be more accurate, but for most users, a 0.09% change in the resulting value does not justify such a massive increase in computation time. So, most users would look at this and simply not bother running any more studies using the more complex configuration, as it just isn't worth their time. For a Formula One team, however, whose resources, from what I hear, are quite plentiful, and to whom fractions of a percentage point in a simulation study can make all the difference on the racetrack, they would likely run all of their studies, including many components that most people would just leave out, and they'll either run the simulation using cloud computing or have an extremely powerful computer dedicated to running their complex studies 24/7. So, since we can confidently say that the results of the studies run using the simple configuration are accurate, there's no need to rerun the fatigue or frequency studies, and we can finally review the end results. Remembering back to our design requirements, we wanted our maximum stress to be less than 400 megapascals, and ours was 315.2 megapascals. So we definitely met that. For factor of safety, we wanted a value of at least 2, and we saw a value of 2.63. So all in all, we can confirm that we achieved our design goals for strength. For durability, we just wanted to ensure the steering bracket could withstand a full Formula One season, which ends up being 100,000 cycles. Our fatigue study tells us that we could actually complete nearly 4 million loading cycles before failure would occur. So we definitely met the design goals for durability. Finally, for performance, we were aiming to design a bracket that wouldn't resonate within the 1 to 60 hertz range, which is a common vibration frequency that the part will endure during a race. Our frequency study showed our lowest resonance frequency was around 2300 hertz, so we also met our design goals for performance. And so, looking at all of the design goals here, so that's for strength, durability, and performance, our simulation results indicate that we have met all three of them. Now, before finishing here, you might feel like something is missing from the studies that I've run. As I mentioned at the beginning of this session, one of the most important things in Formula One is weight, or rather lack thereof. Keeping the car as light as possible means you'll be able to accelerate, brake, and corner faster. And so I'd like to see if we can remove any material from the steering bracket in order to gain some performance. Now, I don't want to just cut a random chunk out of the bracket and call it a day, as there'd be a pretty good chance I would make things worse. So instead of just guessing here, I'll go into my static one study, activate the configuration, and then what I'll do is I'll edit the steering bracket part in the context of the assembly. Or rather, I'll run the design insight plot first. So that's what we're doing here. In the static one study, I'm going to create a design insight plot. And what the design insight plot does is, based on the results of a static study, it shows the elements of the component where the loading is above a certain value based on this slider here. When I move the slider to the left, what you'll see is that it only shows elements with a high loading, so the threshold is increased. And then when I move the slider to the right, it decreases that loading threshold. And so the goal here is to keep decreasing that loading threshold until I have a mostly continuous path on this back face of the steering bracket. So let's keep going. Maybe something like that. That looks pretty continuous there, so I can be happy with that. And then I can hit OK. And so with that, I know that any areas missing from the model currently are seeing less loading than the threshold I set using the slider, which was quite low. And so because those areas are enduring a negligible amount of loading, those areas can actually be removed from the model without greatly affecting the component's strength and durability. So with the design insight plot still showing, I'll edit the steering bracket component, and I want to open up a sketch on this back face here. And in this sketch, what I'm going to do is basically just sketch out a shape that fits within the blue boundaries created from the design insight plot. I'm not too worried about symmetry or anything like that here. I'm just trying to hog out some material to reduce the weight of this component. And so again, just using the boundaries, the blue boundaries of the design insight plot as a bit of a guide, I'm happy with that shape there. So what I'll do is I'll go ahead and extrude this shape as a cut. It'll be a through all cut. Well, that's not what I wanted to do there. Let's try that again. Extruded cut. There we go. Through all. And what I can do now is go back to the model view here to confirm that I actually removed that material. And at this point, it's pretty clear that I did. And so what I'll do now is I'll use my rollback bar to go before the cut. So the cut hasn't been added yet. And I will go ahead and check out my mass properties here to see how much the part weighs before the cut was added. So it's basically 189 grams for its mass before the cut's added. And then after adding that cut, if I recalculate the mass, it's 187.27. So just about 2 grams of mass have been removed with this extruded cut. And although 2 grams isn't much to most people, in Formula One, every single gram counts. And so this is the type of weight saving you would see often in Formula One. And I also want to mention here that when doing a design insight study on a heavier part, the mass of material you may be able to remove can be far greater. So don't expect it to always be such a minuscule value. Of course, when you remove material from a part, its strength characteristics are likely to change. And so you don't want to make a change like this without rerunning the simulation studies. So let's see how this affects our static study here by rerunning that static study. All right, I'll go ahead and run it. Just finishing up here. All right, there we go. And as our results show, in the von Mises stress plot, our peak stress is actually being reduced to 312 megapascals. And this is because the cutout allows the design to flex a little bit more, reducing the peak stress seen in the model. Now, a reduction in stress is not always going to be the case. It's not always going to be like this, where things actually get stronger when you remove material, as usually removing material will weaken the model. However, either way, if the design insight plot is used to decide which material to remove and which material to leave behind, you can be confident that if the model is weakened at all, it will be by a very minor amount. And of course, when modifying the model in any way, you wouldn't just rerun the one static study. You would definitely want to rerun all of the studies you've created for that model so that you can get your updated results, even if it's only a minuscule change. Now, I don't want to waste everyone's time with that, so I'm just going to run the static study that I already did. All right, and so with that, that's actually all I have for you in this session here. So thank you all so much for attending my session. I sincerely hope you enjoyed it and hopefully learned a thing or two.